A large part of what you're going to do in our class is stoichiometry, okay? Reaction stoichiometry. It's a way for us to tell how much of something will be produced, how much of something will be reacted based on the balanced reaction that we have. So, stoichiometry involves using the coefficients, that's why we have to balance it, coefficients in a balanced chemical equation to determine the quantities in chemical reactions. The absolute first thing you need is that balanced equation. You cannot do stoichiometry without the balanced equation. So for example, we've got here, solid aluminum reacts with hydrochloric acid to form an aqueous solution of aluminum chloride and hydrogen gas. We write out that reaction. Solid aluminum, hydrochloric acid, aqueous solution of aluminum chloride and hydrogen gas. And then we balance it. So we see that we've got 2 moles of aluminum reacting with 6 moles of HCl to produce 2 moles of AlCl3 and 3 moles of H2. But what does this mean? This is telling me exactly what is reacting. And this means that I can derive mole to mole ratios. Now, we saw some mole to mole ratios when we did previous work looking within formulas, but now we can actually derive them from the balanced equations themselves. I can say 2 moles of aluminum for every 6 moles of HCl. It takes 2 moles of aluminum to react 6 moles of HCl. I could take 6 moles of HCl for every 2 moles AlCl3. It requires 6 moles of HCl to be reacted in order to produce 2 moles of ACl3. I could say 2 moles of Al for every 3 moles of H2. In this reaction, in order to produce 3 moles of hydrogen gas, I need to react 2 moles of aluminum. I can say 3 moles of H2 over 6 moles HCl. The reactant or product can be in the numerator, okay? As long as I'm using those balanced equations. They all are equivalent to 1. They all equate out to 1. So it's like multiplying a reaction by 1, but just converting the units. I'm just converting to a new species. The coefficients given in the give the reaction recipe in moles. They become the mole ratios, or what I call multiple ratios, and we use them as conversion factors. You can also, so not only can we compare moles to moles, we can compare liters to liters of gas under similar or specific conditions. We'll talk about that in the gas chapter, and molecules to molecules. Because again, remember what a mole is actually representing. A mole to mole is actually representing that molecule to molecule idea, because a mole is telling me exactly how many I have of something. You cannot compare masses. They don't combine in terms of masses. An oxygen, a molecule of O2 weighs 32 grams per mole. A molecule of H2 weighs 2.016 grams per mole. So 1 mole of oxygen is, again, 32. 1 mole of hydrogen gas is around 2, so 16 times smaller than O2. I cannot combine them in terms of masses. I can't use grams. I have to use moles. Coefficients do not affect your molar masses. The molar mass is still the mass of 1 mole of the pure substance. We use stoichiometry with the multiple ratios to account for those coefficients instead. So your molar mass stays the same. We just use the balanced reaction for an additional conversion factor. Here's the strategy we're going to use. First, you need to recognize that you need to use stoic when the example gives you information about one or more of the chemical species in the reaction, and it asks you about a different chemical species. So it says, how many grams of this can I produce if I use up all of this? Or I reacted 5 grams of X, how many grams of Y can be produced? Something like that. You have to have a balanced reaction to do the stoic, though. If it is not balanced, you will need to balance the reaction. And that's because you need those multiple ratios of the species involved to be able to do the stoichiometry. First thing you should do is change your given quantity into moles. It may already be in moles, but if it's not, you need to change to moles. You need to use your mole ratio to convert the moles of the species you have into your new species. And then you answer the question you have. So, given quantity into moles, mole ratio to get to the species that you desire to know the information about, and then convert that into the answer you need. And right now we'll be looking at grams, but we can convert this into milliliters, we can convert this into information about gases, etc., as the stoichiometry continues. So let's work an example. How many moles of oxygen will be produced by the decomposition of 5.8 moles of water? So we're already in moles, so that's convenient. Write down what you want to know. You want to know number of moles of oxygen, and then write down what you're given. 5.8 moles of water. I don't have to convert to moles, I'm already there. But I need a balanced reaction here. I'm like, okay, moles of oxygen, decomposition of water, that's not helpful. I don't have a reaction yet. So let's go ahead and write one out. If I've got water, water will decompose to form oxygen gas, and I know that because it's here, and there's only one other thing listed here in the compound, so it must produce some hydrogen gas as well. Okay, so that's how I know what the reaction is. I know I got to produce oxygen. Hydrogen's the only other thing present. It's going to produce some H2 gas. I need to balance this though. I have two oxygens, so I need two oxygens. Now I have four hydrogen, I need four hydrogen. Now that I have a balanced equation, I can go ahead and use my stoic. I see that 1 mole of O2 is produced for every 2 moles of H2O consumed. That cancels out my moles of H2 and gives me my moles of O2. Calculate it out, and I get 2.9 moles of O2. I had 2 sig figs here. This is an exact conversion, so I need 2 sig figs in my final answer. Look at another one. What mass of hydrogen gas can be formed if 12 grams of aluminum reacts with excess HCl? Okay, what am I trying to find? I'm trying to find the mass of hydrogen. Mass means grams. Unless otherwise stated, it means grams. So number of grams of H2 gas, and I'm starting off with 12 grams of aluminum. Well, I need a balanced reaction because I don't know where to go with this. I don't have my stoic. So aluminum is a metal, so it's going to be a solid. Reacts with excess hydrochloric acid to produce hydrogen gas. And then what else is going to be produced? Well, the other things here are aluminum chloride, AlCl3. Until we get to reaction predicting, I would give you the information to be able to write out the rest of that reaction. I would also say it produces aluminum chloride, but soon you'll be doing reaction predicting, so you'll be able to do this yourself. Let's see, what do you want to balance first? Let's go ahead and balance our hydrogens. I have 2 and 1, so I'm going to put 2 in front of here. Notice that really throws off my chlorides. That doesn't make my chlorides look very good. So I'm going to need a 2 over here for my chlorides and a 6 here for my chlorides. It's the only way to balance it. That threw off my hydrogens though. Now I have 6 hydrogens, so 3 here, and I still need to balance my aluminum. Is it balanced? 2 aluminum, 6 hydrogen, 6 hydrogen, 6 chloride, 6 chloride. Yes, and I cannot minimize the reaction, so that is correct. Now that I have a balanced reaction, I can go ahead and convert to what I want. I need moles here, so I know 1 mole of aluminum is 26.98 grams of aluminum because I looked up at my periodic table. Again, if you don't have one with you, you should always have one with you when you're studying. Go to ptable.com. Great website, has a lot of information, and has a nice periodic table. Now that I'm in moles of aluminum, I can use my balanced reaction to get to moles of hydrogen. I see that 3 moles of H2 are produced for every 1 mole of aluminum consumed. Again, grams canceled. I'm going to put the moles of aluminum in the denominator because I need them to cancel out, giving me my moles of hydrogen gas. I want grams of hydrogen gas. 1 mole of H2 weighs 2.016 grams. And again, that's from the periodic table. 1 hydrogen is 1.008, so 2 of them is 2.016. This gives me 1.34 grams of H2. Moles have canceled out. I've got my grams. I've got 3 sig figs here, 4 sig figs here, exact conversion here, 4 sig figs here. So my final answer has 3 sig figs. Again, very soon you will learn reaction predicting, so you should be able to tell me aluminum chloride will be the other product. But until that point, if I gave you any sort of assessment before that, I would tell you what the other product was here. Okay, what mass of oxygen gas is required for the complete combustion of 29 grams of butane C4H10? Here's one I will not give you the reaction for. This has all the information you need to be able to predict that reaction. So C4H10 is undergoing complete combustion, which means it's going to react with O2 gas to form CO2 and water. Carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. I have 4, I have 10, I have 2, I have 1, I have 2, 2 plus 1 is 3. Balance everything except oxygen first, just in case. I don't know if we need a fraction or not. I won't know until the end. So carbons first, put a 4 over here. That gives me 4 CO2s, which changes this to 8. Hydrogen's next. I need 10 of them, so I need to multiply this by 5 to get 10. So that gives me 8 plus 5, which is 13. I have 13 and 2. This is the clue that everything else is balanced. At this point, everything else is balanced except that oxygen, and I have a 13 and 2. That's my clue that I need that fraction. Again, this becomes the numerator, this becomes the denominator. 13 halves O2 would equal 13. But I cannot leave it like that. I have to now multiply 3 by 2 to get rid of that fraction. So 2, 13, 8, and 10. And if you don't trust me, go ahead and check it. I now have 8 carbon, 20 hydrogen, 26 oxygen, 8 carbon, 16 oxygen, 20 hydrogen, and another 10 oxygen, giving me 26. It is nicely balanced. Now we can actually work on the problem. And now I forgot what we're going to do. Okay, mass of oxygen gas. So number of grams of O2 if I'm combusting 29.0 grams of butane. And notice I'm also very intentionally writing what species I'm talking about in each one, because if you just have a bunch of numbers, you're going to get lost in what you're doing. Write down what species you're talking about there. First thing you need to do is convert to moles. If you don't know what to do, convert to moles. It's probably the right step. Add up the molar mass of butane. You're going to get 58.12 grams of C4H10 for every 1 mole of C4H10. Now I want to know how many grams of oxygen. So I'm going to look at my oxygen. I've got 13 moles of O2 being consumed for every 2 moles of C4H10 being consumed. Cancel out my grams of C4H10. I've canceled my moles of C4H10. I'm in moles of O2. I don't want moles, I want grams. 32.00 grams of O2 for every 1 mole of O2. Calculate this through, and I get 104 grams of O2. Check your sig figs. 3 sig figs, 4 sig figs. Exact. 4 sig figs, 3 sig figs are my final answer. And you've just balanced your reaction. Or sorry, you've balanced your reaction, but you've also just completed your stoichiometry.